Cool. So we had a lot of content to cover in last class too. So I figured probably best off, unless there is anything specific you wanted to review from that, I figured we could continue on with the content that was left uncovered for that. And then if we have time after that, we can also start looking at the sketching of the circular functions, because I know at least one of you guys are into the sketching side of things as well. So was there anything in particular anyone wanted to review, or shall I continue from here?
I think just continue on.
Easy. Okay, so this one's going to cover all of the individual sort of symmetries that can appear in the circular functions, or specifically around where things are located on the unit circle. The first concept is periodicity. So all circular functions are periodic. So essentially, if we were to imagine what the graph of a circular function looked like, it has this sort of wave-like pattern to it that repeats over and over again over a fixed interval. By default, it'll repeat over 2 pi as far as the x domain is considered. Very similar to how a unit circle works, where a full revolution going around one full cycle is done in 2 pi. And so simply put, because of that, anytime you have like 2 pi, any even pi addition to a known value on your circular function, the value ends up being the exact same thing. So we have this known value, sine theta equals 0.43. We can draw a quick little diagram to sort of represent what we have there. We don't necessarily know what theta is in this case, but we do know that it gives rise to a positive sign. So it could technically be in the any of the top quadrants, but just for convenience, we can usually, in fact, in pretty much every case, draw our what's referred to as like our reference angle in that first quadrant. Now, when you add something or subtract something from theta, what you're essentially doing is starting at some angle and then continuing on in either the clockwise or anti-clockwise direction, based on if you're doing plus or minus, and then seeing where you end up. Because 2 pi is a full revolution, 2 pi plus theta just means start at 2 pi plus theta, you end up with exactly where you just started. And that's the gist of it. Works exactly the same for sine and cos. So you can see we get to the exact same xy coordinate there. With tan, it's a little bit different. Tan is not periodic in 2 pi, it's actually periodic in pi. And that's because if you look at how tan works on a unit circle, whenever the signs are matching and the values are the same, because you're doing one divided by the other, the gradients end up coming out the same. Right, so like if you're in this quadrant, for instance, you now have negative y and negative x, but the negatives are going to cancel out. And so instead of having to jump from a full revolution to pi, you actually have identical values on within pi. And so we can sort of see that here. There's 1, there's 1. There's root 3, there's root 3. Even over here, right? Negative root 3, negative root 3. They're already symmetrical in a half revolution as opposed to a full revolution. So it's just a small add-on to that. And we get to see again how like pluses end up working when you have them within the same bracket. So we're told some initial value of tan theta, and we're trying to figure out what this new version of tan is. What happens when you do pi plus theta? Pi plus theta means start at pi and then add whatever your reference angle is. We started with a positive tan, so just by default, we've put the reference angle in the first quadrant somewhere. Pi plus theta means start at pi, and then whatever this theta was that you drew, just mirror it over to this side. And because you are fully separated by pi, you end up with the exact same value. That's periodic functions in a nutshell. I've seen a question come through. Can we do some practice? Yeah, we're going to do a lot of practice on these. This one's on the simpler side because it's just value is the same as value. So practicing just this example, probably not going to be super... Well, we'll give it a shot. Let's see. I think in 6b we got some stuff. Pi minus theta, pi plus. 2 pi. Yeah, we'll continue on a little bit more, just so we can address most of these off rip, and then we can start practicing then. Here's the other versions of the pi plus and minus theta now. And once we go through these, then we'll do some practices on them. So we've already discussed how pi plus theta works. You start with your reference angle, then wherever pi is, you then plus theta. So pi is always on the left. You got your reference angle in the top right quadrant. You're now getting in the bottom left quadrant because you're plussing that version of theta. Basically, the way this always ends up working is you start with what's your value. In this case, its sine is equal to 0.72. So that means that the y value on your reference angle is 0.72. Then you look at this thing. Is it pi plus theta? Is it pi minus theta? What actually is going on there? This one is pi plus theta. So it means you start at pi, add your theta. That's going to put you in the quadrant 3 there. And because we're in quadrant 3, we know that both things are going to go negative in quadrant 3. So whatever we had there, we're now putting negative signs on exactly what that coordinate was. And so whether it was sine or cos, whenever you do pi plus theta, whatever the value is that you have is now going to be the negative of that value. Started with this coordinate, ended with that coordinate, and we just write out the one that we were supposed to understand. If sine theta is that, then whenever you have pi plus theta, you always end up with the negative of that thing. Fair enough conceptually? Pi minus theta, ever so slightly different. Again, starting with our value, sine theta equals 0.72, so we use the y value as 0.72 for our red reference angle. Then we look at this bit, pi minus theta. That means start at pi, but then go backwards by theta. So that's going to put us in quadrant 2 there. Now, what we know about quadrant 2 is only the x goes negative there. Everything else stays the same. And so, because of that, if we're only interested in the y value, because we are interested in sine here, the y, well, it's going to maintain. You can see horizontally speaking, only the x would change in that case. So if you want to do sine of pi minus theta for that particular value, it stays the same. That's pretty much it. Everything else is just going to be a different version of whether it's sine or cos. Yeah, pi plus theta, start at pi, plus theta, look at the x value now because it's cos. Cos pi minus theta, so pi minus theta puts you up here. And because we're doing cos, we look at the x value once again. That's all it ever is. We did this tan, we'll do this one now. So again, pi minus theta puts us in the second quadrant. Only thing that's a bit weird about the tan stuff is it can be a bit harder to actually label the unit circle because labeling the unit circle is done with x and y coordinates, whereas tan is the ratio between them. It's the gradient, y divided by x. So when you're doing these, I tend to keep them as x and y, and then when I flip things around, I just think about what that division would cause. So for instance, we started with a positive tan, which had two positive, like an x and a y. Now that we're mismatching that, one of them becomes negative, the actual values themselves haven't actually changed. So whatever that division is still going to maintain the same number. The only thing that's different is going to be the sign that changes. Those are the things I think about. You can also think about where sine, cos, and tan are positive or negative on your unit circle. So if you know that tan is positive in quadrant 1, 3, and negative in quadrant 2, 4, perfectly fine for you to use those as well. You could even look at like the gradient of those lights that you're drawing. Right, the red line has a positive gradient, the green line has a negative gradient, so tan should be negative for green. These are some little tricks you can use. Actually, there were a few negatives, weren't there? Yeah, there were. Okay, let's do that. And the last few we'll look at before we do some practice here is going to be the negative versions. So what does that mean? So start off as we always have. Sine theta is equal to 0.37. We create our reference angle. It's sine, so y is going to get that value of 0.37. Then we're told to do sine of minus theta. So one way to think about that is to treat it basically the same way as you would do like pi or 2 pi plus or minus theta. This is essentially 0 minus theta because there's nothing in that leading spot. So you start exactly where you started before, but you're just going in the negative direction. Whoops. We also kind of know how this one works as well from when we did the last lesson on this, where those negatives were effectively a reflection downwards. So essentially wherever you drew this, you're just reflecting directly down and you're changing up the signs accordingly. That's all it really is. So broadly speaking, drawing a unit circle, reflecting things around, seeing what quadrant it ends up in, and based off of that, you can make some conclusions based on what the signs of the x or the y coordinate should be. Same thing with cos over here. Cos is going to maintain because it's in the same right-hand side of the unit circle, cos being the x. And for tan, because you're flipping from a positive gradient to a negative gradient, the value is going to go from positive to negative. That's the gist of it. Anything in there individually that needs clarification on like a conceptual level? I'll put the PDF in the chat for you guys to refer to because there are a lot of them. But they all have the same way of solving it. Like we looked at several examples, right? Like if we scroll all the way down here, we've covered all of that. Oh, actually all of this. So like if you think about the number of little equations, that is a lot. But instead of memorizing all of these equations, you can instead use a diagram approach, drawing a unit circle, reflecting things around, and then using stuff you already understand, which is your XY axis to figure out what should happen. Cool. Okay, let's give some of these a shot then. So we'll just go through a few of the question 4 ones. Yeah, part of the challenge is going to be knowing when to use what, essentially. But they all do start out the same way, so we should at least get that far. Okay, so 4a. We're just going to look at the ones that have theta in them, just for ease, because these all have different angles, and basically the ones that have different labeled angles use different unit circles to each other. So we'll just start on with one of them, make life easier. So we'll do the sine theta is equal to 0.52. And we'll just focus on moving this one around a bunch of times. 4a, so knowing that sine theta equals 0.52, we now need to find what sine of pi minus theta must therefore be. That's our goal. Any thoughts on how we could start this one out?
So you can start by drawing a unit circle.
Drawing a unit circle, yep. Perfect.
Just to figure it out. But yeah, you just think about starting from pi, because that's halfway through the revolution. So that would be on the far left, and then minusing theta, which is 0.52 as an angle.
So worth pointing out, 0.52 is the value, not necessarily the angle.
Oh, sorry. Yeah, just as if you minus theta, and then
yeah. So as long as you already know that you would put a reference angle in quadrant 1 for this, sine being positive, you can have some initial theta there, and essentially as long as you know that, then from there you can be like, oh cool, to minus theta, that would mean putting us in quadrant 2.
Yeah. And then because, oh, sorry, that's what I meant. So if you have the sine, you know the value of sine is 0.52, so that's just your y value.
Yeah, that's right.
At the point, yeah.
So
but we don't know what x is.
That's it, yeah. No idea of x, but we do know the y is 0.52 because y is sine, yeah. And then, yeah, we can take it on from here, which is what? How do we finish it
up? You just write it out as sine pi minus theta equals 0.72. Sorry, 0.52.
Yeah. So basically what you're getting at there is that this coordinate can kind of be reflected over. The x does technically change, but we don't care about the x. we just care about the y because we're asked to find the sine of this spot, pi minus theta. So as you said, sine of pi minus theta is also 0.52. Cool. That's that one. Okay, where's the next theta? Sine of 2 pi plus theta. Okay. Sine 2 pi plus theta. I'll start us off with the same reference angle. Cool. All right, 2 pi plus theta. What do we do in that circumstance?
This one, you just have the reference angle you've drawn is just the exact same since you're starting from 2 pi. So
Yep, 2 pi is the same as the 0 location, and so 2 pi plus theta is always the same as just regular theta. Nice. So once again, identical. Cool. Okay, are there any unique theta ones going on? Yeah, there's one more. Maybe two more, actually. Sine of, what is it? Pi plus theta. All right, pi plus theta. Where are we going to end up?
this one, just like the first one, you're just starting from pi.
Mhm.
And then we're adding theta, so moving in an anti-clockwise direction.
Mhm.
So now, because sine is a y value, it's going to be negative, so it would be negative 0.52.
That's it. Yeah, we're in that third quadrant. We're below the x-axis, and so we should have negative y values, and therefore, yeah, negative 0.52. Nice. For this one, I'll change up the number, although it shouldn't really matter. Oh, was that a question? I think I heard something. Maybe not. Just hearing things in my head. Here's a new one. So we had cos x equals 0.68. The only real difference here, of course, being that we're now working with cos and a slightly different number. So when it comes to creating this reference angle, what are we going to label this one? This is just creating the initial thing before we answer any question.
But what are we doing here again?
So this is creating our new reference angle. So before we were using the sine and 0.52, now we're using the cos and 0.68. I haven't given a question to solve yet. This is just setting us up to solve any of the actual symmetries that will come later.
Would it be 0.68y?
That's it. Yeah, 0.68y, because now we know x values. It gets a bit weird when they start using x in the brackets, just because we say different things. When I say x, I'm usually going to mean the x coordinate, even though the angle is technically labeled as x there. But yep, that's that one. Let's see, is there a nice cos? Let's do cos minus x. So that's the one we're trying to solve on this now. Based on our reference angle, where does cos minus x put us?
You'd flip it kind of across the middle, so in the second quadrant.
Second quadrant's this one?
Yep.
Okay. A little bit different, that one. So negative x, when it comes to, it's a bit weird. Because when we think of like our functions, that would typically mean a flip horizontally. It's a bit weirder for circular functions in the sense that when you have a negative on the angle bit, it just means going in a clockwise direction as opposed to anti-clockwise. So if this is angle x, then it ends up being the case that this is angle negative x in here. So it ends up being a flip downward. The challenge being you've got to stop thinking about circular functions as like function function rules and think about it purely in terms of like the angles and which direction they go. But yep, now that we know what quadrant we're in, answering what happens should be not too bad. What actually happens here.
Would it just be 0.68 negative y?
Yeah, 0.68 negative y would be the coordinate, and obviously for the actual answer we would just keep the 0.68. Yeah, we're in the negative y spot, but we're still in positive x spot. Cool. So we looked at sine, we looked at cos, we've looked at all of the individual translations, those sort of starting locations. Let's do a tan one and see how that one works. So we'll do a tan of alpha is equal to 0.4. No question yet, just setting up our reference angle. There's a couple of ways you can set it up. This is actually just pure preference at this point. One way is to have just xy, like that. The other way, if you want to have some actual numbers in there to work with, what you can do is you can convert this into a fraction and then have an equivalence of y divided by x. So 4 out of 10 is the same as 0.4. That means you have a 4 as your y and an x as your 10. Reason being is because then you get to see how the tan fraction actually changes in this case. But either of those notations is fine. It's just whether you want to have numerical data in there or if you want to have pure variables. Because like technically speaking, the x and y coordinate are not 10 and 4. You have to have anything between 0 and 1. This is just there to get the relative magnitudes to make it easier to calculate what you end up with. But okay, that gets us our initial reference angle. Let's do, I guess any of them can be fine. Let's do a pi minus theta. And pi minus theta. That'll be the most interesting one, I think. Well, I guess alpha in this case, I should say. All right, first up, where does that put us?
Yeah, I just had a quick question is it always going to be like theta for sine, x for cos, and then alpha for tan, or is it?
Nah, so the reason why they've used theta, x, and alpha is simply because it's just there to show that those are not like related circular functions. They're not all talking about the same angle. You know, it could be, because any angle is going to have a pair, or I guess a triplet, of sine, cos, and tan that are related for that particular angle. They are just doing that to show that they're different angles and they're not related to each other.
Oh yeah, because otherwise it would be like kind of sine, cos, tan, or those values at the same time.
Yeah, if it was like sine theta, cos theta, tan theta, not that it would really change things, but you know, if you did have sine and cos theta, then you wouldn't need an x and a y anymore. You'd have both in that case. Which honestly I think makes a better question because it means you have to actually be looking at the thing. Because when it's like this, it's not too bad because there's only one number there that you can use. You only got to think about whether it's going to be positive or negative. So I think, yeah, it might actually be better questions if they did make them all the same angle, because that way you'd have to think about, do I give the x or the y in this spot? But anyway. So with this one, we got to first figure out what quadrant we end up in. That should be more or less the same as what we were doing before. We have pi minus alpha. Where's that going to put us?
in quadrant 2,
Quadrant 2 is correct, yeah.
and the coordinates would be negative 10, 4.
Yeah, so you'd end up with negative 10, 4 there if you're using this version of the notation. Yeah, negative 10, 4. Absolutely. Pi minus alpha. This is where it gets a little bit funky because we now need to figure out what happens to tan here. We don't actually have a tan value necessarily located in there, but we sort of split it up and put it in there. We've now just got to reassemble it. So what does that actually mean that's happened to tan? Got a new set of coordinates since we've flipped things over. We know our cos and sine from there, kind of. We just got to recombine that into getting our tan. What's tan going to end up being in that second quadrant?
9 over negative 10.
9 over negative 10. That's my fault for writing my 4 as a 9, but yeah.
Oh, sorry, my bad.
No, it's
Yeah, 4 over negative 10.
It's fine. That's me being bad at writing. Yeah, 4 over negative 10. And then simplified, you'd probably want to put it back in the same format as the question. So because we had 0.4 there, you'd maybe want to write that as a decimal of negative 0.4. But yeah, both are the same. One ends up being negative 0.4. Yeah. That's
Wait, so for tan, like when we're like kind of drawing out the angle, it's just the same process, but just at the end we're doing the sine over cos.
Yeah, precisely. So literally every symmetry property that we use will use this approach of drawing the reference angle, seeing where we end up, and then, yeah, from there making some conclusions based on what's happened to the x and the y. So as long as you're good at now thinking about tan as gradient, effectively, rise over run, y over x, then you're essentially just doing like one final conclusion off of that. You look at the x and the y, and then from there you can calculate your tan. For a lot of them, tan is just going to flip sine, whether it's going to be positive or negative. In fact, literally all of these are just flipping signs on each other, which, come to think of it, we have looked at all of them now. We've looked at what happens when you have negative angles, pi plus and minus theta, 2 pi plus and minus theta, and we did it for sine, cos, and tan. Do we want to practice any more of those that you're seeing on question 4, question 5? Or are we happy to move on to something or some new symmetries? We do one more tan? Yeah, sure. Let's get a new tan going. So let's go. So you can even use the same circle technically. We'll go with tan of pi plus alpha. So we still have this reference angle from here. So this bit here will be irrelevant for it. Only this bit will be relevant specifically. Pi plus alpha, where's that going to put us?
Third quadrant.
Third quadrant, that's it. Pi plus alpha, down here, pi, and then alpha.
And then the coordinate's going to be negative 10, negative 4.
Yep, negative 10, negative 4. And then from that conclusion, we can calculate our tan to be
4 over 10, which you can simplify to 2 over 5.
Yeah, 4 over 10, 2 over 5. Same thing with the decimal as well, if you wanted. Probably, yeah, just like a minor nitpick there for exam writing. Keeping it in the same form is typically slightly higher regarded as marking. Now, yes, you will both get the same mark, but this is more so like if you're competing at high study score levels. When you're on that border, these are the things they look at for like accuracy of answer versus just did you get it right. But yes, you've done the math and calculations perfectly fine. Yeah, cool. Those are all the unique ones, I believe. Let's move on now. So now we're going to look at things that are slightly different. We're still going to be using the same overall idea, but what we're going to find with the quarter period formulas, these pi over 2 plus minus thetas, is where things are going to start to get a bit weirder, because now what we're going to end up noticing is the x and y coordinates are actually going to flip on each other when you do the quarter of the period. The reason why this happens, for those of you who were here for when I looked at the unit circle the first time, I discussed things in terms of their relative x and y locations. All right, like I was discussing how do I fill out the unit circle, and I was thinking, okay, if you look at like the x locations of these, the shallower angle is going to go further along the x, so the biggest x value should go first, then the next, right, going in a descending order there. Similar for like the relative y locations, we're climbing up, so the smallest should go first, then the next biggest, then the next biggest. When you're doing pi over 2 and then minus theta, it's basically this property here, where if your theta was pi over 6, for instance, you would have this coordinate. In fact, I have a picture of this. If your theta was pi over 6, you'd have this coordinate. Right, it's the shallowest of the angles. If you then do pi over 2 minus theta, because you're now coming from perfectly vertical as opposed to perfectly horizontal, you're getting the opposite effect. The location of the x and y are perceived as flipping, but in reality it's just because you're starting at a different location. You're climbing down y values rather than climbing up y values, or vice versa for x. So we get this apparent flip that's going on in the x and the y. This x is root 3 over 2, this y is root 3 over 2. This y is a half, this x is a half. We get this sort of flip there. That's what you now need to think of when doing pi over 2 related things. So not only do you have to think about what quadrant do we end up in, but then flipping it. So it's just going to be one more addition to what we just did. Figure out our reference angle. It's always going to be in the first quadrant. No question has ever been written differently. If you're plusing theta, you're going to end up in that left quadrant. If you're minusing theta, you're still going to be in the right-hand quadrant. But because we started pi over 2, the x and the y locations are now going to flip. From there, everything else becomes the same. And yeah, we have, again, some known values here to watch out for. So pi over 2 minus pi over 6 does in fact get you pi over 3. Pi over 2 plus pi over 6 does in fact get you to 2 pi on 3. So there's a precedent that we can actually look at on our unit circle, or if we have it memorized, we can think about it that way as well. So let's have a look at a few. So first up, we're going to have a look at the pi over 2 minus theta type things. Again, we have our initial reference angle, so we draw that in. You'll typically draw these a bit shallower than the rest of them, just so you have room to put it in, just in case it ends up in the same quadrant. And it's also helpful because you don't want to think about things in terms of like full half revolutions. It can be another way of distinguishing between whether you're just flipping the signs or flipping the values as well. But yeah, we draw it a bit shallower, and especially because it's minus theta, because when you start at pi over 2 and then go backwards, well, you need to be able to put them both in the same thing. It was just a personal preference to draw this one shallower. You could draw the red one steeper, and then therefore the green one would be shallower. It literally doesn't matter. It's just there as a visual aid. But yeah, because it was pi over 2, we're now from our 0.72 comma y, flipping that to y comma 0.72. That's why you'll see that these kinds of questions will be written as going from cos to sine. You only ever look at one or the other. I see you got a question?
Yeah, I was wondering, like, is it going to be common to have questions that actually ask us to say like draw the unit circle, or is it more just a method?
This is a
means
method.
to the ends.
Yeah, you won't see this anywhere in the book. I don't think so anyway. I mean, they draw this sort of stuff, but if you have a look at how they, I mean, I guess, yeah, well, they do discuss it in the book kind of like that, but they put it all the same, all on the same circle. And so looking at that is less than pleasant, I would say. But technically speaking, that is a full condensed version of what I've just discussed here, how all of these things flip over each other. But yeah, like if you have a look at how the book is describing things, it just says find values, and even in here, it should probably also just say find values. Yeah, find the value of. Yeah, there's not too many of these kind of questions. So yeah, it's purely just a method, basically. Yeah, okay, that's the pi minus theta there. For cos, again, whatever, right? So this time we have the y value, and therefore it's going to flip to an x value when we do our pi minus theta. Pi plus theta, so again, depending on what you start with. In this case, we started with our cos. So pi over 2 plus theta is going to put us there. Because it's pi over 2, we need to remember to flip this around. And I, in the diagram, will draw this in 2 stages. If you don't want to, you don't have to. Again, it's a visual aid, just so you can sort of see the progression of it rather than try to do too many steps at the same time. So start by flipping and then mirror it over. So you now have what was once a y value is now an x value, and what was once a positive x value is now a negative x value. But because, again, we were doing sine here, we didn't really care about the fact that it was negative. It only matters in the second example where the value goes from here to here, and then finally as a negative. Again, you can just ignore this bit, as long as you know to flip and make, as long as you know to flip anytime you have a pi over 2 type thing, then that's fine as well. Any questions about that one so far? Because tan is going to be another step of complexity. Okay. So why is tan going to be a step up in complexity? Well, because again, what we're looking at is what happens to x and y. We then have to then conclude what's going to happen at tan based off of that. Which is why you'll often see, if it's not already in a fraction, it's ideal to put your tan into a fraction. Let's actually have a look. Yeah, okay, they have 0.7. So it'll be an easy enough decimal for you to convert into an equivalent fraction. And the reason why this becomes doubly important, specifically for pi over 2, is because when you flip your x and y, you're flipping your numerator and denominator. So you have your initial point. In this case, you'd be labeling that 7, 10, I suppose, if you wanted to label them with the actual numbers that came from here. And then you'd end up having 10, 7 for your x and y, which you then put, again, in their correct spots. In other words, just flipping the numerator and denominator, and depending on what quadrant it ends up in will determine what signs you put in there. If you end up over here, you're going to be negative, right? Because not only have you flipped the x and y, but you've also made one of them negative. Because you've got that mismatch in the division, the net result is going to be a negative division. So tan becomes negative. We'll pause there for a moment. Any questions about that one? Three pi over 2 is the same idea. I don't actually have it written here, but whether you have pi over 2 plus minus theta or 3 pi over 2 plus minus theta, it's the same idea, because once again you're on that quarter boundary. So pi over 2, 3 pi over 2, both of them have that flip idea, and then whether it's negative or positive, once again, is going to determine based on what quadrant you ended up in. The last one, which will help you answer question 2 stuff, is the Pythagorean identity, which is literally just your a squared plus b squared equals c squared, expressed as the circular functions within the unit circle, right? Because we know that cos of the x sine is the y. We can shove that into our Pythag identity, and because our hypotenuse is 1, well, we can put c equals 1. So it ends up being the case that sine squared plus cos squared is equal to 1. And we can use that for these kinds of questions. So that's sort of what we were kind of discussing earlier, which was, how they had like the different angles for like x, alpha, theta. This is where they do make them all the same. But what they say is you only know one of the three, and your goal is to figure out the other two. As long as you have sine or cos, you can then use the Pythag identity to solve the other one. This is pure algebra at this point. If sine is 3/5, then we now have 3/5 squared is equal to cos theta squared plus 1. Cos is now the only thing left of the equation, so you just rearrange to get cos on its own. So expanding, subtracting, square root both sides. Only thing that's going to be a bit weird here is the plus minus that'll now be attached because you are square rooting. To handle that, you just want to look at the domain that's assigned to it. So notice this one says from pi over 2 to pi. If we look at our book, we also see that all of those come with domains as well. Because if there's no domain, both of these could potentially be valid, whether if cos is on the left or the right. But because we have pi over 2 to pi, that's this. All right, pi over 2 is there, and pi is there, so we're in the quadrant 2. X can only be negative in quadrant 2, so we're only going to take the negative solution of that. We get our cos is negative, we get our sine is that, sine divided by cos gets you your tan. That's all of those, and realistically, you've only really learned like 3 things to do. You create your reference angle for all of them. You learn how to do integer values of pi, plus or minus theta. Basically, all you're doing is flipping the sign of whether it's sine, cos, or tan becomes negative or positive. This one here isn't even actually new. It's the same stuff as what you were doing before with when we had this unit circle stuff, whether you go the negative approach or whether you, where is it? Oh, it's in a different document. Whether you find the positive value and then flip to a negative. And then this one here, which you're then also flipping the location of the x and the y. You're replacing them with each other. So even though it looks like a lot, I to this day cannot like look at one of these and tell you what it refers to. There's just so many of them there. My first point of call still is just to draw the picture of what that would end up looking like, and then I'll come to a conclusion. Because look at how many there are. There's so many. You're not going to memorize all of this. And if you do, you're better than me. Cool. Let's get some practice in. So once again, you have the PDF if you want to refer to the last few that we just did there. We'll start with the sine x one, just to keep things easy enough. So sine x equals 0.3. We'll skip the ones we've already kind of done, and we'll just focus on the pi over 2 and 3 pi over 2 type angle stuff. We all know how to do the reference angle at this point, so I'll just sort of get that one done. X, comma, 0.3. And what's the first thing that has x in it? Cos pi over 2 minus x. Cool. Cos pi over 2 minus x. So we have this as our initial thing, and we want to figure out what cos of pi over 2 minus x would therefore be. How are we going to do it?
So it's pi over 2. So we'll start at the top, kind of.
That's good.
And then since we're minusing x, we're going to go in a clockwise direction.
Yep. That's good.
And the coordinate would be not 100% on the chord here.
Okay, that's fine. So there was one key difference that I mentioned that was weird about pi over 2 versus the other ones that we did. Do you remember what the main thing is?
Uh,
I'll pull up the intro to it as well on the screen share. So I won't show you the specific one, but I'll show you the discussion on it. I mean, I guess this is the exact example, kind of, which... Anyway, it'll test your reading comprehension at the very least. So what happens to the coordinates when you have pi over 2 minus theta?
oh, yeah, stopping the x and y coordinates.
Swapping the x and y, that's it. So based on our example, that should end up with what?
0.3x.
0.3 and x, yep. That's it, flipping the locations. So any pi over 2 type, anything that can't be simplified into an integer value of pi, you do a flip of the x and y location. Now from that, we can determine what cos of pi over 2 minus x should be. What might we get as a final answer?
Point 0.3.
0.3 is correct, yeah. Because all of this graph stuff that we're doing is finding out where this spot is on the graph. And we get it, cos, then we do x. And yes, it's a bit easy with these examples because there's only one value there left, so it's kind of hard to miss it. Which is kind of why, again, I feel like these would be more challenging questions if they gave you a cos and sine pair to work with. Because that way you'd have to definitely determine, hey, do I have x or do I have to do y? In fact, maybe I'll just sort of make one up. This isn't going to be super accurate, but I'm going to say cos x equals 0.7. They're not actually directly related that way, but just to step up a little bit of complexity, I'll put in another value there as well. Which, by the way, this is going above and beyond what's in the book. So if you can do this, then you'll be fine. Cool. Okay, where's the next x thing? We did that one already. Let's do... Sure, let's do that. Let's go 9 pi over 2 plus x. So again, x, so we're still using the same reference angle, even though I've cheated a little bit and made it a bit different than what we had before. Still, the idea is the same. First, we've got to figure out where does pi over 2 plus x put us, what quadrant, then what actually happens to the coordinates.
Would be in the second quadrant.
It was a bit muffled there. What quadrant, sorry?
The second quadrant.
Second quadrant, yes, that's right. So it's going to put us up here, roughly. Angle x. And yeah, all I need to do is label it. So we're going to go off the basis that the x is 0.7 and the y is 0.3 for our initial coordinate. This flip, what's that going to get us to? there's two things to consider. One is, what does pi over 2 type angles do to the coordinates? And the other is, what does the quadrant do to the coordinates? So we could even just answer those individually, if that's easier. Let's start with the one that we already know. What does quadrant 2 mean for our x and y coordinate? Okay, seems like we're a bit over it today. Yes, so our quadrant 2, we're going to have negative x's and positive y's, essentially. So that tells us what quadrant 2 is going to behave like. All we're going to do now is figure out, based on the pi over 2 type angle, what do we then do to write these in? And if you look at the inherent symmetry here, whether you're doing pi over 2 plus or minus x, because they are equidistant from each other, just one is going in the opposite direction to the other, because they're essentially in the same spot, it's effectively a reflection. All right, this is a reflection across the y-axis. So treating this like a reflection across the y-axis, it's nice to already have this point here. If we were to treat this like a reflection, what would we therefore have the
Negative.
points?
Negative. Sorry.
You're still lit up as green, but it didn't come through, I don't think. Oh, and now your mute's bugging out. That's really weird. I think you said it, but it seems like your audio's just carked it. I'm seeing it bug out a lot. Uh-oh. But yeah, so we would end up with the negative of this x, so 0.3, and y is going to maintain.
0.7.
Yeah, there we go. I heard that. 0.7. Nice. Yeah. We now have our coordinate. That's going to be this, negative 0.3, comma 0.7. All that's left to do is say, hey, what's sine of that spot? Sine being the what part of the coordinate?
Sorry, what was the question?
So we're just wrapping up the question, which is, we've now got the coordinate. We're told to find sine of pi over 2 plus x.
Negative 3.3.
Sine is the x or the y?
Also, the y, sorry, so it'll be
Yeah.
0.7.
So 0.7, that's better. Yeah, there we go. Good thing I did this change, because when there's only one number there, it's easy enough to just say the number. When there's two numbers there, you've now got to double check and be like, hang on a minute, we're doing sine or cos here. Which one's which? So yeah, I'd even in, well, it's kind of hard to actually practice that on your own. You got to kind of make them up like me. But again, this is going above and beyond. In the book, you only have to worry about one or the other, not both, being there. Okay, and just so we can hit all of them, we'll move on to question. Should I? No, I'll do a quick demo for a 3 pi over 2 type thing. So let's say we wanted to do cos of 3 pi over 2 plus, yeah, why not, plus x, whatever. Again, we're using x, so we still have this initial reference angle. 3 pi over 2 plus x. Does anyone know what quadrant that puts us in? Starting at 3 pi over 2 and then adding, oh, I think I heard something.
Is it the fourth?
The fourth quadrant, yeah, that's it. 3 pi over 2 is here, adding x puts us in here-ish. Nice. Okay, now from there, we just got to figure out first what happens to the signs, and second, what ends up being the values there. So as far as quadrant 4, what are the signs for the x and y?
Positive x, negative y.
That's it. You got a positive for the x and a negative for the y. And then yeah, all we're going to do is remember, hey, what happens with the pi over 2 type things? Yes, it is 3 pi over 2, but technically it applies to anything that doesn't simplify into the integer. Which you only ever look at the pi over 2 type stuff as an example of that anyway. So as far as what the actual net coordinates are going to look like, we start at 0.7, 0.3, and we end up with
0.3, negative 0.7.
0.3,
So then,
negative 0.7. Yeah.
so then the answer would be 0.3.
And the answer, yes, 0.3, because you don't want to do the cos of that spot. Perfect. There you go. Nice. Cool. Okay. Now we'll wrap things up with this. This is basically just algebra at this point. It's using the cos squared plus sine squared equals 1 identity. And we're going to have a look at the, I don't know, let's do question 2a, for instance. So we're told cos is equal to 3 over 5, and our domain is from 3 pi over 2 to 2 pi. Our goal is to figure out sine and tan. Yeah, we should be able to do both. So sine x equals what? Tan x equals what? How are we going to get started?
Do we use the Pythagorean identity for sine?
That's, yeah, so we're going to basically sub in the value that we have and use it to solve sine. Absolutely. So 3 over 5 all squared plus sine squared equals 1. 3 3s are 9, 5 5 is 25, plus sine squared equals 1. Sine squared equals, what's that, 25 minus 9. Math, hard. 25 minus 9, what's that, negative 16? No, positive. Square root plus minus 4 on 5. Yeah, that gives us a bit of a weird result there, plus minus. Only one of those is going to be valid. How do we figure it out?
Do we have to refer to the quadrants?
Say that again, sorry, I think it was a bit muffled.
Do we have to refer to the quadrants?
Yeah, that's right, referring to the quadrants, absolutely. So what does the quadrant that we have here tell us about the value?
It's in quadrant 4, so negative.
Quadrant 4, so negative. Yeah, that's right. Sine is the y, and y is negative in quadrant 4, so we only have negative for that. We have sine, we have cos. We can now use that to find tan. Sine, cos. How do we create tan out of sine and cos?
I think was it sine over cos or cos over sine?
One of those. Which one are you going to bet on?
Sine over cos.
Sine over cos. Yep. So 4 over 5 divided by, what's that, 3 over 5. I would typically prefer, in my working out, to do an actual division symbol between these, because if you just do 4 over 5 divided by 3 over 5, that's a bit messy to keep track of. When you have an actual division symbol in there, it keeps things as split as possible. That way you can now start doing the arithmetic a bit easier. I doubt we'll need another example of that, but if you guys need to clarify anything, even if it's not this one, something else as well, I'll be here for the next couple of minutes or so, should you wish. Otherwise, yeah, we've effectively caught up to the the stuff that we didn't cover last time. Next week will be all out sketching, as per the curriculum. Unless you guys want to do something else, of course. Thanks for coming. I'll leave you to enjoy the rest of your day.
Thank you.
Thanks.
Thanks.
Thank you.